What's up, people? I'm going to be talking to you today about Le Chatlier, or Le Chatelier's principle. And this is about equilibrium in a closed container in a reversible reaction. And this is an expression you're going to learn, which is the K, or the rate the reaction moves in one direction or the other. Now, here is a reversible reaction, and it's maybe the most famous one ever used when we talk about Le Chatelier's principle. And it's called the Haber-Bosch process. And this is basically how we can have so many humans living on the face of the earth. This is the way that we can get nitrogen from the air, and because 78% of the air is nitrogen. And we can combine it with hydrogen, and we can make ammonia. Now, this indication right here, this ammonia, this is fertilizer, okay? So we wouldn't be able to grow crops without getting nitrogen from the air. This is a reversible reaction. What is a hint to you that this is a reversible reaction? That's right, the arrows go back and forth, okay? And we're going to call these the reactants, all right? And we're going to call this the product. And the other thing is this makes ammonia and a lot of heat, okay? So does that mean this is exothermic when we're talking about going to the right? Does that mean this is exothermic or endothermic when we're going to the right? That's right, it's very, very exothermic. As it goes to the right, it has a negative delta H as it goes that way, okay? And you should know this from last week. All right, let's balance this bad boy. What would the balanced numbers be? That's right, 1, 3, 2. And before I move on, I want to tell you, this guy right here, I need you to look him up and watch a quick video, Great Minds, okay? And type in his name, Haber, and watch the SciShow on YouTube. Type in Great Minds SciShow Haber, and you will hear a very, very, very interesting story about a very conflicted man who ended up feeding the world while trying to learn how to murder people. Very, very interesting thing. Worth your time. If it was a regular year, you'd hear a lot about him. Okay, and all the kids that are in school this week, they're going to watch the video about him. So you should watch it. It's 9 minutes long. It's worth your time. Okay, so as we're going to the right, nitrogen gas and hydrogen gas make ammonia gas and heat, so it's exothermic. Now this reaction can also run backwards. It's called a reversible reaction. Can also run backwards, and then two ammonias can split up into hydrogen and nitrogen. So this way it's synthesis, and this way it's what? This way it's a synthesis reaction, and going to the left it will be, that's right, decomposition reaction. Okay, now what we're going to do is understand that there is a certain way to talk about reactions, all right? And now I'm going to draw this again. Now I'm going to talk to you about equilibrium. What does that mean? You may think that equilibrium means if we're having this reaction occur in a closed container, that there's an equal number of reactants as there are products, but that is not what equilibrium means. Equilibrium means that the rate in which this reaction is going to the right and nitrogen and hydrogen are making ammonia is equal to the rate that this reaction is going to the left. That's what equilibrium means. And there's a number that's a little bit complicated, but we can assign a number to that, and that number, the rate at which it moves back and forth, is called the KEQ. Now, if a reaction goes to the right or to the left in an unbalanced fashion, then you will have a KEQ. If you let this reaction go to the right, it will have a K that is either above or below the number 1. If the reaction is greater than the number 1, then it favors the products. In other words, you're making products faster than you're making reactants. If the reactant If the KEQ, or the rate at which it goes back and forth, is lower than the number 1, then it favors the reactants. If the KEQ is below the number 1, then it favors the reactants. In other words, you are making, its reversible reaction is happening at a higher rate than the forward reaction. So if the KEQ is a number higher than 1, you're making this faster. If the KEQ is a number lower than 1, you're making these faster, okay? So what if you were looking at a reaction and it said the KEQ was equal to 1 times 10 to the negative 14th? Would you say that favored the reactants or it favored the products? That's right, it favors the products because this number is lower than 1, okay? And this is something that'll look more familiar to you in just a little bit. Now, let's say we have a pressure tank here, a pressurized tank at a chemical fertilizer facility. Now there's a valve here that can let nitrogen in, so we open this valve up and you end up with a bunch of nitrogen gas in here, right? And then we open this valve up and it lets the hydrogen in. What would naturally happen in here, if there's any pressure at all, this is a pressure gauge, okay? And we'll pretend this is hooked up to a compressor that can add pressure to the system. This is a pressure gauge. If there's any pressure at all in here, then some of these N2s and H2s will crash into each other. And guess what they're going to start making? Some NH3s, right? Because this is the reaction. N2 plus H2 makes NH3. And these are all gases. These are all gases, remember? Okay, 1, 3, 2, gas, gas. So in this cylinder, if we let nitrogen and hydrogen in, they're naturally going to collide and they're going to make some ammonias, some NH3s. Okay? Now, if we look at the rate at which this happens, the KEQ is very, very low. And what that means is it is much more likely for the ammonia to split up into nitrogen and hydrogen than it is for the nitrogen and hydrogen to crash into each other and create ammonias. Because the KEQ is way below 1, okay? The KEQ is very, very low. Now, we're going to stress this system, okay? We can let some nitrogen and hydrogen in. We can change the pressure. Another thing we can do is we can put a little heater down here, okay? And we can heat it up. And we have another valve here. We can let out some ammonia when we want it, okay? So we can change the temperature, the pressure, and the concentrations of nitrogen, hydrogen, and ammonia. Those are the 3 ways that we can stress the system, okay? The 3 ways we can stress the system. Now let's think about something here. If I opened this valve and I let a bunch of more nitrogen come streaming in, boom, a bunch of more nitrogen comes in, isn't it more likely now, since there's more nitrogens in here, isn't it more likely they're going to collide with the hydrogens? That's correct. If you add a product, if you add some nitrogen, then this system will, what we call, shift to the right and make more ammonia. Because it's more likely, because there's more nitrogens in here. So if you add a product, you get what's called a shift to the right. More ammonia is made, and then we go right back to the same K. Remember, the K isn't the concentrations of each, it's the rate at which the reaction goes back and forth. So if we add a bunch of nitrogen, we'll get a shift to the right. And then after the shift to the right is complete, we'll go back to equilibrium. Now, what could we do then? If we wanted to, we could open this valve and let out some ammonia. Guess what? Letting out ammonia would also produce a shift to the right, as long as we had enough nitrogen and hydrogen in here. Why? Because the K is going to remain the same. If we let out some ammonia, that's more room here for more nitrogens and hydrogens to collide, and they'll balance each other out. If you're confused, keep watching. Here's how this is worded. When we talk about concentration, if we add more reactant, adding a reactant produces a shift to the right. In other words, if we add more of this, then we're going to be able to make more of this. That's stoichiometry. Does that make sense? Does that make sense? What if we added more of this? Yep, we're going to get a shift to the right, and we'll be able to make more ammonia in order for this system to stay in balance. So there's hydrogen and nitrogen and ammonia all in this closed cylinder at the same time under pressure. If I let in more nitrogen and more hydrogen, guess what? It's more likely you're going to very quickly make more ammonia. That is called a shift to the right because you're making more of these. Very simple. Again, I'll repeat, what if I pulled some of these out? Then guess what? More nitrogen and hydrogen would crash in to each other and make more of them again, because remember, the system is going to stay in balance. The shift is brief, and then the KEQ, the rate at which it goes back and forth, remains the same. Okay, whatever number it is, this stays steady if you're messing with concentrations. Next, we're going to change temperature. Okay, now we're going to talk about temperature here. Now, when we look at the Haber process, the Haber-Bosch process, we see that it is very exothermic, right? As it goes to the right and it makes ammonia, it gives off a lot of energy or a lot of heat, okay? So it's very exothermic. It has a negative delta H. Now, temperature is going to affect how this works. For this thing to go to the right, it needs to be able to get rid of a bunch of energy, okay? Now, if we heat it up, then it's going to actually prevent it from doing that. And you may be like, why is that, Mr. Perkins? Well, if you add heat to it, okay, then it can't give off heat. Here's a way to look at it. You know how you have a car engine, and we do everything with your car to try to keep it running cool. It's got a radiator, it's got a fan, everything. But if the radiator runs out of water and the fan breaks, then your car will overheat and it will stop working, right? The reaction, the gas combustion reaction in your motor will stop working. How do we keep our car, which is very exothermic, how do we keep it running? We keep it cool. So adding heat actually crushes this. So adding heat to an exothermic reaction produces a shift to the left. Adding heat to an exothermic reaction produces a shift to the left. And look at what it also does. It also changes the K. Temperature is the only thing that actually changes the KEQ, the rate at which this happens. Adding heat to an exothermic reaction would lower the K. If you took heat away from or cooled an exothermic reaction, then that would make the K increase, okay? So if you added heat to this, you would get a shift to the left, and the rate, the equilibrium rate would go down, okay? Or the equilibrium constant would go down. If you added, if you made it colder, then you get a shift to the right, because if you made it in a cold place, then it can get rid of energy, and the K will actually go up. So temperature is the only thing that will change the K. Now the last thing we can do is change the pressure. Let's think about gases and pressure. See, I have soda in here. It's under a lot of pressure. See that fizzy fizz? I've got the cap on. Having that pressure is actually keeping these bubbles to a minimum. If I take the cap off, lots of bubbles, right? So more pressure, having the cap on, means less bubbles. No matter what, I can shake it up like crazy, right? And I'm going to have some bubbles, but not as many as if I opened it up and lowered the pressure. So pressure means add pressure and you get less gases, okay? So if we're in this closed cylinder here, and this is our formula for what's happening in the cylinder, if you look, we have, I call them bubbles, we have 4 gas bubbles on the left, 1 nitrogen and 3 hydrogen. So you have 4 gas bubbles on the left. As the reaction runs to the right, you only have 2 gas bubbles, 2 ammonias. So remember, this reaction is reversible. If we added pressure, would this shift to the right or to the left? Correct. Adding pressure means less gas. So if you had this formula right here, adding pressure would produce a shift to the right. You would end up with more ammonias in there. So the number of ammonias in there would be more. It would shift to the right for a second, and then guess what? The KEQ would equal out. Pressure does not change the K. The only thing that changes the K, or the rate at which this moves, is what? That's right, temperature. So adding pressure does not change the K. The equation just shifts to the right. You end up with less gas bubbles, okay? And then it stabilizes again, all right? So if we hook this up to a pressure pump and increase the pressure, we'd actually get more ammonia in there, okay? And then if we let go of the pressure, if this is a valve, we let pressure off of it, then it would shift to the left, and you would end up with more nitrogens and hydrogens. Does that make sense? So you really need to watch the lesson. I'm going to do all this stuff again in class and film it and post it. And this is your ed puzzle on equilibrium. And some things you need to know is there are 3 ways to affect what's going on with a reversible reaction. You can change the concentration. You can change the temperature. And you can change the pressure. Okay? They can cause shifts to the right or to the left, depending on the type of reaction you have. And the only one that can change the K, or the actual rate at which it happens, is temperature. Let's do a couple here for Funzo. Check this one out. Nitrogen gas and oxygen gas make nitrogen oxide, or dinitrogen trioxide in heat, or it can reverse and dinitrogen trioxide can go back into oxygen and nitrogen. We'll pretend that this is happening in a closed container, all right? As this goes to the right, is it exothermic or endothermic? Yep, it's exothermic as it goes to the right, has a negative delta H as it goes to the right, because you can see it's producing heat over here, okay? What would happen if I added some oxygen? Okay, add O2, going to get a shift to the right. If you add some more of this, you're going to end up making more of that. And then the KEQ would do what? That's right, it would remain the same. Okay, what if I removed some N2? Which way would the shift be? Would it be to the right? That's correct. Removing nitrogen from the tank, if this is imbalanced, then this would have to break down and go back and produce some more nitrogen. So removing nitrogen, shift to the left. What would happen to the K? It would stay the same. What if I added pressure? Well, then we would have to balance this. Okay, the reaction is 2 nitrogens and 3 oxygens can make 2 of these. So adding pressure, That's going to be a shift to the right because there are less gas bubbles over here. There's 2, 3, 4, 5, and only 2 on this side. So adding pressure, shift to the right. What would happen to the K? Nothing. It would stay the same. Last one. What if we cooled this? What if we removed heat? Would we get a shift to the right or to the left? That's correct. We get a shift to the right because it's very exothermic. And if we cooled it, then it would be able to give off more heat. It would be in a cooler environment. What would happen to the K? The K would go up because temperature actually does change the K. That's it. You got a worksheet and another. You can watch me teach this lesson. Bye.